When you have two objects that move together, their accelerations are constrained to be equal, so that the acceleration of one must equal the acceleration of the other. This is what we call an acceleration constraint. It seems simple, but it's a way to link two different equations, and it allows us to solve a more complex system as a series of equations. Consider a situation of a car being towed by a truck. In this case, if the rope is under tension, and we assume that the rope can't be stretched, which is our typical assumption, then however much the truck accelerates, the car must accelerate by the same amount. Therefore, the constraint is that the acceleration of the car must be the same as the acceleration of the truck. Because the accelerations of both objects are equal, we can drop the subscripts and call them AX for acceleration in the x direction. In fact, we'll see that when we are looking at them, looking at equal accelerations, we can use the same amount for the acceleration in different parts of the same problem. One example of that is here, where you have two blocks that are connected by a rope that goes around a pulley. In this case, the signs of the acceleration can be different. If block A is accelerating to the right, it should have a positive acceleration. However, if block A is moving to the right, that means block B has to be moving down. And if it's moving downwards, according to our general convention of up being positive and down being negative, the value of that acceleration should be negative. So in this case, the acceleration constraint is that the amount that block A accelerates in the x direction is the same as the negative amount that block B accelerates in the y direction. Typically, if you set up your axes in a way to make these work, it's not usually an issue because you end up with the same value of A that you can substitute algebraically from one equation into another. You'll see an example of that in the associated exercise. So to round out our problem-solving skills using forces, we begin by identifying the objects that we're interested in, which objects are the system in question, which objects we are trying to, whose motion we're trying to understand, and which objects are part of the environment and are around but are not part of what we need to do. We can make simplifying assumptions. For example, if a block is moving across a table, we can assume acceleration is only horizontal and that vertical acceleration would be zero in that sort of situation. The next is to draw a picture. Pictures always help understand what's going on. It's an important part of the picture is to set up the interaction diagrams or the force identification diagrams that we've seen previously in this chapter. Those let us set up separate free body diagrams for each of the objects that consist of that are part of our system. Once we have a free body diagram, the point of a free body diagram is to be able to use Newton's second law to create equations for each object. But the trick here is that once we have these Newton's second law equations, these force equals mass times acceleration equations for each object, these equations aren't independent, they are all linked to each other. And so the way that we can solve them is to equate the magnitudes of our action-reaction pairs. We'll see in particular a lot of times you'll have a tension that is pulling to the right on one block and it's pulling to the left on the other block, and you know that the tension has to be equal, or has to be constant throughout the rope, and so that will let you reduce a variable in your equations. You also, this is also the point to use acceleration constraints to be able to say that the acceleration in one part of one of your equations is equal to the acceleration in another part. Again, it gives you a bridge that allows you to connect these multiple disparate equations and solve them as a series of equations. Once you solve for the acceleration, like before, we can use kinematics to find velocities and positions, find the motion of the object after the fact.